All right, guys. All right, guys, let's get the lecture started. Too high? Too high? Would you able to hear me? What's this? Okay, good. So, yeah, hope everyone have a good weekend, and welcome back to lecture. We're going to today mainly talk about PCB design and a couple other interesting things. To start with, announcement. We are currently, obviously the most important stuff, we are currently grading the exam 2. We're about 95% done, and we will hopefully post the grades tomorrow. Anyone have any questions regarding this? Okay, cool. So another interesting and exciting part is the student presentation. It will be starting this Thursday. We do apologize for the short turnaround time. Normally we will have one additional guest lecture, so that you have like a full week to be the first couple groups to present. Unfortunately, because of the enrollment of the class this year, we had to start the presentation one lecture earlier, so that we can fit all the groups within the lectures we have, with maybe one lecture buffer time. We'll see how things goes. If we have enough time, then we could arrange something else. The attendance is required, and we can talk about this in a little bit more detail. Again, starting this Thursday until essentially the week before the final demo. And it will be roughly 4 teams per lecture, and each team have about 15 minutes, give or take. So 12 minutes presentation plus 3-minute Q&As. You are required to meet with the teaching team one day or a couple of days ahead of your presentation. We assign the 30-minute sign-up slot. Please come prepared, and then if you have any questions also feel free to ask. During that preparation, you should at least have your like a close to finished version, or at least all the points that you want to talk about and all that. So it should be like a more or less towards final-ish stats. And let me show you the. So if I show you the sign-up sheet we have, in case you haven't checked out, okay. In case you haven't checked out, we have the sign-up sheet here with all the slots that we provide every week, as well as the topics and the team that assigned to this. We will take consideration that some teams present earlier than the others, so I guess the gradings and expectations will be slightly varies, but still try to, as you usually do, just try to bring up the content and introduce to your peer classmates. Has everyone checked out their assignment and the team, like the meeting slots assignments as well? Okay, cool. Okay, let's get that out of the way. All right, so overall, this will count about 60% of your final grade, and generally everyone on the team will get the same grade, unless you don't really talk or you missed your presentation. If you do have to miss your presentation, let us know as soon as possible, so that we can have with your accommodation letters or like doctor notes or whatever. The whole breakdown will be 25% preliminary and 75% in class. Preliminary basically means the 30 minutes presentation slots with us, with the instructors, to show that you actually thought about it, and then you have like a well-prepared plan and like reasonably prepared content for the presentation. The 75% in class, 50% of that will come from the instructor sitting in the room. And 25% of that will be coming from the peer review. So we will be sending out a Google form link, so for the entire class, so that you can basically rate the presentations by however matrix you want. And we're not comparing, within the class. We don't have to rank, the number one gets 4 credits, number two gets, it doesn't work like that. It's just everyone have their own, so everyone have the same standard. So it's totally possible that 4 presentations during one lecture, they all get, 4 points, or all of them doesn't show up really well. So it's not like we're comparing each of the lecture. You should at least attend 6 out of the 8 lectures to get the full participation credits for the rest of the class. So, yeah.
So one of the 6 lectures, will that be the lecture that we present? Can that count as one of the 6?
Yeah, that would be count as one of 6 as well. But in that lecture, you still need to rate the other 3 teams. So, yeah. Bless you. Any other questions? Okay, cool. So some preparation, I guess, strategies. Total 12 minutes of presentation. So depends on how many content you want to put on your slides. You're looking at like 10 to 20 slides. And the presentation structure, you can just generally consider as, what, why, how. What means, what is this sensing modality? What is this device, or what is this peripherals? And why do we need it? What is good for? For different applications, or to sense something either other sensors can't sense, or sense something better than the other sensors, or sense a very specific narrow application, but like way better than the others, etc. And how basically, how to use this sensor modules or peripherals or protocols you're presenting. And it will be great that you can include both the general strategy, how people normally would use this, as well as your specific sensors. Like, for example, if you present IMU, you could use various different ways, I2C, SPI. It would be great to have your specific sensors that you chose. The ones maybe you got from Bosch or from like SparkFun, etc., and then how you interact with that sensor in your own project. So that's like the how. And of course, maybe like some limitations. What are the domain that this type of device works great? What's the boundary, and what in which use scenario that it doesn't really work that great, and you should not use that, etc. And stay engaged actively. There will be questions probably either during or after the presentation. So be prepared that some questions from your classmates, and try to have the content to be more interactive, because it's not going to be on the exam, so you don't have to stuff a lot of the written content into this, I guess. Just try to stay engaged. Any questions regarding the content, like the student presentation part of the class? All right, cool. So next, we're going to move on to the main topic for today, around the PCB design. So before we dive in, we could take a quick look at how people do the early stage circuit prototyping nowadays. And not surprisingly, most people use breadboard for that. It's very easily to just plug and unplug your components, switch components, and you can reposition your components as well. This, you could call them like high function flexibility, or like high reusability. Basically, any components you use for any circuit, unless you short circuit it or break it, chances are you can reuse it for other applications. And there are a bunch of like availability and affordable options out there. Like, these are the sensor modules you can just use to directly plug into the breadboard package. They are usually called DIP package, during line package, referring to the space that between each of the pins. However, while the testing the function on physical prototypes and or products is very easy to do with the breadboard, they don't usually integrate well with the physical form of your final devices. So this is usually where the final or like a higher fidelity prototype comes in, which goes to the custom PCB. This is a, I guess, heart shape or triangle shape, however you call this. With custom built PCBs, your prototype or your device will be much more integrated together with the physical form factor. But of course, it has some like drawbacks. It's pretty much impossible to move components, and the soldering and desoldering can be a hassle. If you want to reuse some of the components, they actually have this whole industry going on. I think in Shenzhen, they take some of the after-party components. Like if you have some broken electronics, they take off some of the components that's still usable from that deposed PCBs, and then make like a resale black market out of it. You probably wouldn't run into this. I only ran into this once during the COVID, because for whatever reason, the entire world is short of 32-to-1 mux. They say that it's because of the car industry take all of them. So we were in desperate need of that ADG 731. Not sure if you guys know that. The only 32-to-1 mux chip out there. So some contacts put us in contact with some dudes in Shenzhen, and he were able to sell us for like $100 per piece, about 10 times more expensive than what you get from DigiKey. But these type of market exist. Other things is the whole thing is going to be more time consuming, because you do have to. Time consuming meaning refers to the iteration. The design iteration are going to be much more time consuming. Usually turnaround time is about at least a week or two, depends on where you order them. But yeah, low function flexibility on the PCB end. They do have something kind of in between, the proto board. Some people call it the perf board. So basically, you could essentially use all the like the breadboard components and directly solder onto each of these through holes. And although it's still very hard to move the components and the soldering and desoldering, but it's going to be much better than the PCB, because you can actually change the trace or change the circuit layouts underneath much easier, because the PCBs, once you're done with it, it's pretty much fixed. There are some tricks you can do, but largely fixed. So if you want to make a PCB printed circuit board, at the end of the day, if it's just a set of wires that connect a set of components, electronic components together, and a bunch of things needs to be considered on how you lay out them, and which type of even like the software to use, how to place the component position, etc. We'll go through those process basically. First, some basic terminologies for the PCB design. Traces are basically the wires that you use to do the layout, and layers meaning different planary that goes into a PCB, which can be used to lay down traces or place the component on. The place component on usually refers to the top and bottom layers, because usually I don't think you can really put components in the middle layers. Through hole is basically holes that left on the PCB that use for like pin components that to go through and solder down. The common ones are the those header pin connectors you see. You can use that to connect to a different, like Arduino, or connect to your own STM32 through jumper wires. So those are the typical use case for like through holes. You could also have the through holes there, so that you can solder some like the dual line package, basically the component that's used for breadboard, to be soldered onto the PCB board as well. Not that common, but if the space is not too much of a consideration of yours, feel free to use that. And we also have the via. So via is a hole that connects different layers together. So it's also a hole, but like much smaller than the through holes you will see. The surface mount is basically all like the surface mount package, SMD components, however you call them, basically are the devices that, or components that goes to be placed on the PCB surface. Usually those tiny components They have their own package name. For example, these ones are likely 0603. That's just the dimension of that capacitor. So these things tend to be much smaller and compact to give you like a more integrated and compact layout to save space. And we have the pads. So basically, this is where you the naked copper or naked tin space you left there for you to solder the components onto your PCB board. To put them in context, these are where what do they means on a very simple design PCB. You have those silver look like pads and traces are usually the wires and the pads or footprints that are used for soldering your components onto. They might oftentimes look like silver because it's coated with some other alloy or other metals to make it harder to be oxidized. But underneath, it's usually copper. The solder mask, usually green color for most of the PCBs, but nowadays you do see a bunch of black ones or like matte black ones. I think it's led by Apple. I think they're the first major manufacturer that make all their PCB board matte black. So if you want to just deassemble your MacBook or iPhone, you will see like a matte black PCB inside. And the holes that go through. So small ones are the via holes. These ones, the drill holes are not the through holes we talked about. These ones are usually there for mechanical purpose. So imagine you need to have this thing to be connected to a screws or something to be mechanically attached to something. Those are usually the space left for that. The through holes for the pins to go through are those ones, the four that's much smaller than this but bigger than the via hole. And if we have just look on the side of the PCB, this is a 6-layer board. Chances are you guys probably wouldn't use this complex design for your PCB. Most commonly ones are, at least for this class, would be probably, and also for 73, will probably be 2 layers because it's much easier to design, manufacture, and order. Nowadays, it's quite common to order 4 layers as well. Usually, the 2 additional layers are one for ground plane and one for VCC or VDD. It's easier for your circuit layout so that you don't have to have power route going through the entire, all the components. All you need to do is have a little via that goes to the power plane that connects to that components to power it up. For the ground, it's usually better to have large ground, so the signal integrity is generally better, and it's more prone to the environmental noise. So if you have, say, like a MacBook, you will notice that, not sure if you did, but the entire case of this computer is actually ground, so the metal piece, just to give it more prompts to the environmental noise. For the layers that are not ground and VCC plane, they're usually used as additional space to put your wires. Because if you think about it, the top and bottom layers, they only have limited amount of space for putting your wire layouts. If you have a lot of wires that needs to go parallel with each other for a long distance, not sure why you do that, but in case you need to, you might not have enough space on just the top and bottom layers. Any questions regarding this? This is, I think, a PCB that's is medium to more complicated side. The most PCBs you guys design should probably be either 4 layers or 2 layers. Okay, so let's do this the reverse way. First, I will show you how the PCB are manufactured, and then how you would go about to design a PCB that generates whatever file that needs to be generated. So, from a manufacturing perspective, the first step or the the essential files is need is called Gerber file. It's basically the geometry that represents the the size, the locations, and all these like paths locations of your PCB. And it will usually look like something like this. And then from the industry perspective, you will essentially tell the manufacturers what type of raw materials you would like to use for your PCB. The most common ones are this FR4, 1.6 millimeter thick, and then laminate copper materials. It's very common, and if you see like one of those green PCB board, chances are it's done through one of the FR4. So for the manufacturing process, first, they will use like a drilling machine to have all the holes that's needed to be drilled on your PCB design. In the Gerber file, it's actually multiple files. They usually get into one zip, so there are usually 1 or 2 files that's specifically for the hole locations and how big each of the through hole or vias that needs to go through. And then we'll have this electroless copper be dispensed onto the whole board, basically a thin layer of copper, and it's chemically disposed onto that. So at this stage, everything is connected except for the hose. And then it will be a photoresistant image that's been projected onto that component. So it's UV sensitive, and then so that all the traces or the space that needs to have the copper stay on will be left there. And then through another electrochemical process, it will be placed another layer of usually tin to make sure that the plated copper is not going to be etched away during the follow process, which is this etching process. Basically, you place this into a electrochemical bath, and then it will take away all the unwanted coppers from the PCB layer you have. And then it was then coated with liquid solder masks to have the whatever color you wanted to have. In this case, the most common ones, the greens. With that, you would the manufacturers will put on the legends, or they usually call it silk screen. Basically, the labels that you will go onto your PCB usually are what each components are with their, if it's resistor, is it R1, R2? If it's a capacitor, it's C1, C2, and if it's like a jumper or connector type, it's usually JP1, JP2, etc. This is so that the engineers or programs later, they will know what this component is and have a good correspondence from the manufactured PCB to the schematic or like the circuit diagram. Essentially tell you, what this board is doing and how you are supposed to, interact with it. And then you can also, if you have extra space, you can also put whatever you want to put on this. I think since last year, my student in my lab, they start to put our lab logo on all the PCB we send out. Doesn't hurt, and it doesn't cost any extra money. So, if you have additional space. Again, then we have this surface finish, basically to additional layer to protect the copper from oxidization, so that this board can presumably be last longer. And depends on the cost budget you have. You can choose different type of surface finish metal. If it's a high precision needed device, you could choose to have gold to be used as the surface finish, so that it's more stable. It's just generally better. Not sure why gold usually makes things better, but in the case of PCB, it actually does. And then this is some post-processing from the PC manufacturer's perspective, because usually you manufacture a bunch of these PCBs together. You will see that when you order them, probably the minimum number will be like, what, 5 piece or something? And then if you order 10 piece, it will roughly cost the same money because they usually manufacture these in batch. And if you're from industry, you're making thousands or even like way more than that PCBs. So they usually count something like this before they roll out to you. So essentially, the manufacturer have to like cut these individual PCBs from like a binary they're used for the mass manufacture. You can also do this by just peel it off by yourself. How is the manufacturing process looking? Any questions? Good. Yeah. There are also some other ways of etching away the unwanted copper, for example. In industry, in the nowadays manufacturers, the etching one is the most commonly used ones. If for like say smaller batch manufacturing, or if you want to do something with like a little mini machine, you can also essentially melt away the unwanted part from the copper. So you essentially dig out all the traces from a copper surface rather than etching everything away chemically. Yeah, so some components that's quite good to have. The VS that we briefly talked about, this is usually the component that used to connect different layers. So it's very small. It's usually just planted through a hose, but small, so that doesn't usually get in the way of the component placement. You can choose to have them either masked or naked. Masked meaning you will have this this surface finished green part cover the top of the via, so it's more, I guess, contained. But the reason you might want it to be naked would be that it's easier for you to debug on a naked via hose. Imagine each of these vias can be one of your nodes on your circuit. So if you want to know if this component is getting the right signal, etc., the vias can also can serve as a good connecting point from the PCB board. So usually, if you're still doing like the iterations, you're not finalized on the PCB design, the first couple versions of you would probably have the via hose to be naked. For the final versions, obviously you will cover everything to just have a better signal integrity in general. Okay. So with all that, how do you actually design a PCB? Generally, there are these 4 steps. First is creating your circuit schematic, and then you place your part, and then you do the routings together, and then you generate the files for the manufacturing. The generating file part is basically generating the Gerber files that's needed for the manufacturer. By the way, you don't have to take notes. We will release this after class. First will be creating the schematic. This is just to show that how each of the components, devices, passive and active components are connected together. You should be pretty familiar with this by now, based on all the 215s and then some of the other classes you take. So basically, you will have something look like this, just a schematic file that shows what are the list of components used in your board and how they are logically connected. Normally, you will label some of the lines as well. For example, if you use I2C SPIs, you will normally label what that single line is, SDA, SCL, etc. So why do we need a schematic? Usually, it's drawn to be readable, right? So when you do your schematic design, a good practice is to have something that can be readable by others. It's similar like when you write your code. Why do you put comments there, right? so that it's readable by other programmers or designers, etc. And generally speaking, the schematic will be much easier to fix bugs or electronic connections than to have like a PCB layout. Because on the PCB layout, you already have the component physical location set on a constrained space. But on the schematic, you don't have a physical constraints or how big you can, like you don't have constraints of how big your canvas is, essentially. Next would be after you have the schematic figured out, usually, people would have the schematic tested on breadboard or protoboard or however you test it. So usually at this stage, you should know that you have a working circuit. Next would be place the parts. You need to place the footprints on the board. So not necessarily, the thing you actually need to place is not the dimension of the component. It's the dimension that this component is going to take in order to be soldered onto this PCB, which is usually refers to patterns or footprints of that component. So a lot of people, especially if you're like a hardcore EE people, you will see this. They see this as like an art form. How you would nicely place these components and then connect them together. You don't have to make them look super pretty, but general rule of thumb is that you should have the components that work together closer to each other. And you should have, if you have analog and digital part of the circuit on the same PCB, you should probably have the analog part to be on one side and digital part to be on the other side. And anytime if you need to have like a lot of parallel wires go with each other, you should have that wire to be shorter as possible and then also compact with whatever components that needs to connect it to. Sometimes the EDA tools, like the electronic design automation tools, will do the placement for you. But so far, no one seems to really like that, or at least, yeah. But if you don't have a lot of constraints on the space, that can serve as a good starting point, actually. Yeah, so just some more information on the footprints. Usually, each device have footprints that will show exactly how they look, but it is also, and usually they are in the libraries of your EDA tools. However, it's also possible that some of these more custom device or components that don't sell a lot, then it's also possible that they don't have those. So in that case, you actually have to build or draw your own footprint. Any questions so far? Okay, cool. So the next will be actually routing then. A routing is pretty much a connection or electronically connect all the components on your PCB board. There are some general design tools, general design rules that includes you should usually minimize your trace width if you are compact with space. You should usually minimize the spacing between the trays and holes. Again, if you are constrained by the space. But if you, there's also some minimum requirement for each of the components, usually showed in their datasheet. And these rules might vary by different manufacturers. So they have. Sorry, let me rephrase this. So these design rules, they have a few design rules. There are sets of design rules that for you as designers, there are also a set of design rules that set by the manufacturer. The minimum trace width, minimum space, minimum space between holes and vias, etc. These are usually set by the manufacturer. So that's the thinnest wire they're able to fabricate for you. And for you, it's more like depends on how many space you have, and you should connect them accordingly. There are some unit of measure confusion in the PCB. This is due to historic reasons, just like a lot of the measurement unit in US. So a thou means a thousandth of an inch, and millimeter means a millimeter. A mil means a thousandth of an inch. So just a bit confusing. Make sure you have the unit correct. Either it's the standard millimeter or units, or you make sure you use essentially chose your units correctly in your design tool, and then when you do the manufacturing, also chose the correct size units. A little bit of more on the trace width. Usually, for the go-to wires you have, the minimum that they can do from the manufacturer is about like 6 to 10 mils, and for your own design, you should usually try to do like 50 mils for like power and ground, and 25 for like everything else, unless specifically mentioned by the manufacturer. This is usually to help that to make sure there's not too much resistance during the traces, and the signals will go up and down as you require it to be. Remember one of the questions from our exam, if the signal is not going up to as fast as you want, chances are it's probably too much resistance, too much impedance, depends on it's AC or DC. That's being on your circuit. It's also possible that there are some additional capacitance that's been built up on your circuits, and that's usually because of the wires you have on your PCB might be too close to each other, and then they go together for too long. So that have this interconnecting capacitance that's built up, and then that can slow down your signal transaction as well. But yeah, generally, some reference you can have, if you have like a 10 centimeter trace, not sure why would you have that, it's quite long actually, but if you do, it needs to be 10 mils width if it needs to carry about like 1 amp of current. Similar here is, so we also don't want the traces to be just as wide as you want, because usually they take a lot of space. One of the main reasons to have a PCB is to have everything to be more compact, right? So if you then chose to have all the width of the traces to be very wide, then it's kind of defeat the whole purpose of having a PCB. For the beginning, a couple ones you design, it's totally okay to just start with something large. But as you gradually getting more practice, you will see there's like this trade-off between the trace width and your overall integration of your device. If there are cases that you have like a wire needs to go through like 2 holes or like other pads that's very close to each other, it's also not unheard of to have that small parts to be a little bit like thinner than the rest. If it's not a very high frequency signal, it's usually okay. So you usually will start with something like this. It's you can call them rat's nest, or I usually call them air wires. This is auto-generated by the EDA tools. Basically, you start with the schematic, and then you place the component location on, let's say, this space. And then all those wires should be automatically generated and kept connected during the entire design process. These are essentially showing you which pins are supposed to go where. So like the logic wires, logic air wires that's being like displayed on your PCB design. And then you will just, based on that, to do your routing. And whenever you have a additional, like 1 wire that's been connected on your board, that air wire will just disappear, so that you kind of always know that, how many percentage you have achieved, etc. Nowadays, most of the EDA tools, electronic design automation tools, offers the auto routing functions for you. So you can also just have an auto route for you to be at least as a starting point. Chances are they might have like a few wires that's not being routed, but usually if you have enough space, they usually does a pretty okay job. There are, of course, routing quality. This is one of a good example on the left, and then like one of the bad example on the right. So you usually want it to be straight, short, and efficient. So this one basically go 2 lines and probably down under the components, and this one goes around the components and all that. In reality, for your final project, or even for like 473, they probably doesn't make that much of a difference, but it's just good practice once you move on to more complicated designs later. And then you have the generating files part. Basically, a set of files like we described before. Each file describes something different, like copper on given layer, and the silk screen, solder masks, as well as the the drilling hole and place and pick locations, like where each component goes, etc. These are all in Gerber format. It's pretty much like a machine code that was used for the machines too. It's like a G code to give like location informations, the traces, informations, etc. And usually you just zip off them and send it to the PCB manufacturer. It's usually also good to consider to have your design files with it, so that when their engineers inspect your Gerber file, if they run into some like quick questions, they have something to refer to. So just give like a higher level, I guess, workflow. You start with like a schematic, and then this is obviously like way too complicated cases. But then you have all the location placed, and once the location is placed, all the error wires are still there, showing you the logic connections of any given PCB design, and then you finish the routing. And this one happens to be a 6-layer design board, which is probably too complicated for a while. Any questions on the general design flow for PCB? Yes.
So, like I figured with manufacturing, that generally, they just like accept some files and then put it into some computer program and let the machines run. But you're saying like engineers actually inspect the files to make sure everything looks good?
Yes. So if you open, let's say, well, you pay for that, but yeah. If you open, like, say, a go-to, say JLC, I think that's the manufacturers that we order PCB for you for the class. So you can do like an instant quote or whatever. So yeah, these are just a lot of these like design choices you have to make before you even place the PCB order. And one of them, I believe, should have a, let's see. I think there's a, yeah, so there is an option there you can choose to have them to look through the files for you, or not. They just, yeah. They also have by default, they do a continuity check for your fabricated PCB to make sure they come out right as you designed. Any other questions? Okay, so that's the general manufacturing pipeline as well as the design pipeline of a PCB. which tool you're actually going to use. This refers to the EDA tools. There are a bunch of electronic design automation tools. There are a bunch of options out there. There are some open sourced ones and non-open sourced ones. And non-open sourced ones, including like Eagles, they got acquired by Autodesk and discontinued a few years ago, and now become integrated into Fusion 360, and Altium designers, and some open sourced ones, including like FreeSync, KitKat. I can show you some examples here. Yeah, Eagle used to be open sourced, but then got acquired and became non-open sourced. It's pretty decent tool. They usually have it's quite widely used, and if you go to the SparkFun, a lot of the SparkFun or Adafruit, you will see that a lot of their sensor modules actually. This is actually a very useful tool, in case you guys are interested in a bunch of those sensors. So if you just go to, like say, random sensors, you will see that in the document, so they will give you the schematic file as well as the board file. That's for a lot of these sensor modules. See, so this is a schematic file. This is the Eagle file. So one cool thing that Eagle did before, together with SparkFun and I think Adafruit, is that almost all the sensor modules you can purchase from them are open sourced in the Eagle design, Eagle form factor. Sorry, the Eagle file format. So you can actually design this, download this thing, and then open it up in Eagle, or nowadays import it into Fusion 360 to see exactly what's the board file. Board file meaning the placement and the routing, as well as the schematic file. So you can learn how each of these sensors works. They used to be like a pure 2D view tools. Now they have like 3D view that go with it together. You can see roughly as like a visualization or preview to see what it looks like in after fabrication. So this is like the 2D view, and then you can have it in like a 3D rendered view to see what your sensor actually look like in the end. This is the board file. This is the board file of a 9 degree of freedom, I think, IMU sensors from SparkFun. And then we have the Altium Designer. It's not open sourced, pretty professional tools, and it has its own generic 3D viewers, and it supports the command script. Oh, also the Eagle or the Fusion 360 also supports scripting capability. So you can write your own script and then let the tools to run automatically. For example, you can build your own auto router if you want. Similar with Altium designers, and it also able to import Eagle files. So if you are curious about any of those sensor modules on SparkFun, you can also use Altium designers to do that. I think that, generally considered Altium designer is a more well-rounded design tool compared to the Fusion 360 or the Eagle, also because they cost more. So, but one good thing is that I think as UM students, you can pretty much access it free, the Altium Designer. So if you want to design something more on the complicated side, 4 layers or even plus, I think Altium Designer is probably a very good tool to use. Yeah, so the board file in 2D view, and also they can render the board in 3D. And actually, they allow you to do the editing in 3D as well, to drag and drop components, etc. It looks fancy, but most people don't use that, don't do it in 2D, in 3D, because it's hard to get it accurate, but still cool to have. There's also this NI board and multisim. It's not open source. It's a lot of industry people use this. I actually haven't used this myself. So, but it's a very decent tool. It have a lot of simulation environments that allow you to simulate how your board would perform under different like working or simulated working environments. Another very decent tool. Another tool that I think in the past few years, a couple years, that gets a lot of attention is these online design tools, namely the Easy EDA. This is cloud-based, so you don't have to really install it on your local machine. You just open it on the browser, and it's actually partnered with JLC PCB, the pretty big chip manufacturers from, I think, Shenzhen. Usually, it's also supporting the script, but usually the function it has is going to be not as powerful as Altium Designers or Fusion 360, as you probably could imagine. But if you just design something like relatively on the less complicated side, like 2 layers for sure, 4 layers, if the 2 in middle layer is just ground and VCC, then totally go for it. It should be no issue at all. And a huge plus is that if you're considering PCBA means PCB assembly. So essentially, someone help you solder all the components. So the PCB assembly service, then this is actually quite good tool because it gives you almost like a real-time stocking, like a stocking of the JLC PCB. So like when you do your like board design, you know exactly what are the components that's currently available at their stock, or something you need to order in advance. So if you want something super quick, then just pick the ones that they have, and then send the files to the JLC, and they will do the board manufacturing plus the assembly for you. This is just a screenshot taken from the online design tool. Pretty decent, and it's getting better. One open source tools I think worth mentioning is this KitKat. Again, you can import the old Ego design files into this, and it supports scripting in Python. It used to be a bit buggy, but nowadays it's actually getting quite good because of a lot of these programmers or contributors that helps to maintain this this tool. And a very interesting one, it's called Freezing. It's, again, open sourced, but it provides like a breadboard plus PCB together prototyping view. So basically, you can have like some like Raspberry Pis, Arduinos, etc., as a board that imported directly to the system, and then have like a breadboard design on top of it to help to just connect everything together and run simulations on this tool. So I would still consider it as PCB-ish approaches. So yeah, so I included this here as well. It's largely used as an education tool for like circuit building as well as like early stage PCB design. Any questions regarding any of these tools? Okay, cool. So, what are the additional ways to do this? Not necessarily or exactly PCBs, but generally build these more complex or compact circuits onto existing objects or onto a surface. This is more on like the researchy side, but you could do what they called conductive inkjet printing. This is actually essentially you just put those special inks, usually some nanoparticle silver inks, into a conventional inkjet printer, piezo-based. This is one of the printer that I used to have, a Canon one, and I swapped the color cartridge with that ink. And this is the type of circuits you could get. I think this is a Arduino board, essentially. This work originally was done at Georgia Tech, I think. So very interesting paper. A lot of things can be, so the whole workflow is pretty straightforward. You just have like a 2D printer. And all these traces you design in as a SVG file, essentially, or anything that's similar to that, and assign the corresponding like colors and dispense level, essentially how much ink you want to dispense on each of the location. And then that will be printed onto a sheet of paper or a sheet of some like plastic sheets, etc. So the ink they used is they're having more manufacturers for this now. The ones that we used to use, it's from Mitsubishi. I think they stopped manufacturing this about 2 years ago. There's a Austin-based company picked up this work and then manufacture, I think, tens of different conductive inks that can be used by different type of inkjet printers to directly print out the circuits, essentially. Obviously, the benefits here is super fast, very fast printing. Usually you can have a PCB or PCB-like circuit design in a matter of minutes. And then the 2D design process, it's usually relatively easy because you just draw the circuits, but you do have to have some like electronic knowledge for that. The drawbacks on this is it's usually just one single line design, and I can show you some of the prototypes that we built in the last using this method, if it plays. Or it doesn't play. Okay, give me 1 sec. Let me just reopen this. Okay. Let me jump to the So yeah, basically you could have any of the designs outputted from the EDA tool actually. So those files you can also directly import it into like a SVG file, and that can be directly printed on those special sheets of papers. It is, you probably noticed, it is quite challenging to actually connect the components to the circuits. So it would be usually great to use this as just connecting part. If you do want to have SMD or through-hole components attached to those circuits, there is some additional process you need to do. In this way, we have like a Z tape. It's a tape that's electronically conductive on the Z directions to use to essentially connect the components footpad to the circuits. But anyway, let's. There are also other even more easy way to do this. Silver pens, so it's similar as before. It's essentially a bunch of ink, mixed with some nano silver particles that you can directly draw on paper or on like sometimes on PCB board as well. This, I think, originally was used as like a quick fix or quick debugging tool for some of the PCB boards. So you can essentially, if you have some pads that's supposed to be connected, but you did not connect them. So you can use this to like just connect them for testing. It's not going to be stay there for a while, but for your test to see what's the next iteration of the PCB should look like, this tool should generally serve as a pretty decent tool. So yeah, very easy to use. As long as you can draw, you should be able to draw out the circuits essentially. And by making different shapes of the components, you can also build more complex circuits. For example, capacitive touch screens. If you just draw them in these like this layout, and then have 2 layers of them attached on top. So yeah, the entire circuit is pretty just drawn, and then if you can use it as a capacitive touchpad. We also have layering, or like laminating. So basically, you have this vinyl cutting tools. It's very similar manufacturing process, if you think about it, as the etching or like the PCB manufacturing. Instead of using the chemical, you use a vinyl cutter to cut out the traces you need onto the sheet that's supposed to go on. The substance or the sheet can be various different materials as you like. You can even build almost like a flexible PCB with limited curvatures with your circuit. To just show, you can Stanford Bunny, everyone loves to use this as a show off for the geometry complexity. So these type of things can actually be used to generate onto like more concurved or convex surface, such as the Stanford Bunny. Of course, it takes some manual work, but compared to 1 week to 2 weeks turnaround time on the PCB manufacturing, this is much faster as a design iteration tool. We also have like conductive yarns. So you don't necessarily have to always have your circuits to be on like a rigid, the silicon-based stuff, right? You can also have them on soft fabrics. And this is one of the implementations people does. They actually have a set of toolkit of the sensor modules, namely this one. It's called LilyPad. So they make this entire toolkit with all the connecting pad on the outside, specifically tuned to be connecting with the conductive thread, so that you can, connecting the wires on the clothing or fabrics much easier. They have like those basic sensor modules built, IMUs. A bunch of those, some environmental sensors. This one, I believe it's the microcontroller that they have with their toolkit. I think this work was done at Media Lab, if I'm not mistaken. We also have the screen printing. So not sure if you guys play around a lot with this, but you could have the screen printing process is basically, you have some layers, and then you have a mask, and you press it over, and then essentially what's the through part of the layer will be staying on the bottom substrate, right? So it's pretty straightforward, and then you can just place the conductive paste and then brush it over. It's essentially the same process as stencil. I'm not sure if you guys know this term. So if you order a PCB and you don't want to order the PCB assembly service, you usually order a stencil that have those little draw out holes that you can be matched exactly onto your PCB. So you have the conductive paste brush over, so all the naked pads or footprints have just enough solder paste on it. So you can use like a oven to bake the entire PCB instead of manually solder one-to-one. Using similar technique, we can also do spray painting. So there are a bunch of conductive inks out there. It's no surprising that some of them can be sprayed. So instead of having a mask or stencil onto the desk, you just place it on wherever you want to print, actually. And then when you attach to this, and you just spray paint out the circuit onto that substrate. And whatever left there is it's essentially a functional circuit underneath. And to just protect those circuits, you usually also have some covering or protecting layers attached on top, so that it doesn't get oxidized that easily or get sprayed off. Pretty neat, right? I think we put it out on one of the walls in my previous lab, and no one complained about it. And apart from those conductive, those spray paints that usually go on more rigid substrate, you can also have some other. I think this one called PWESS. It's almost like a flexible type of conductive inks that you can essentially spray it onto like soft, in this case, couch, and then they become like invisible after it's dried, and you can just. Normally you have like a stencil thing, but this is just for showing, and you will have like a very decent connection, because the width of you have a large freedom of what's the width of the traces you would like to draw. Yeah, this is just a quick example of showing how you could have worked with it. Essentially, you have like a capacitive sensor on the couch, so it knows if there's anyone sitting on top of it, and you have like a whole over capacitive sensing. Essentially, depends on how close your hands are or any human bodies are to that. It gives a distinguished signal. You can use that to, control TVs or anything. Another thing is you can also use 3D printing to print out essentially 3D circuits inside of your, object design. There are different levels of conductive filament available. This is the I think one of the most commonly used conductive filaments. It's essentially PLA or plastic infused with some carbon particles. So very easy to print, usually works, but often the conductivity of this type of filaments is not that great. It's usually it's conductive enough to light up an LED or to be used as a capacitive touch sensing. To give you like a reference, the amount of resistance probably generated through this one trace through that little button there, it's going to be in tens of K to hundreds of K ohms. So, but you have the freedom of just drawing your circuit in like a much more free form. Rather than just 2D, you can just embed it in essentially whatever shape you want. And some people decide to print it onto a PCB, onto a breadboard for whatever reason. But anyway, so that's for like more commonly used conductive filaments. More like state-of-art conductive filaments, we have this electrify. So these are super conductive. Usually it's about like 0.006 ohm per centimeter. Usually, so it's quite conductive, but the downside is it's actually not that. It's pretty hard to work with. So if you ever think about using this filament on any of your final project or like future projects, feel free to reach out to me. We can give you some like hints or some suggestions on whether you should use it or if your geometry is just too complicated for this. Another downside is the pricing. So 100 gram of this thing costs $215. And maybe now they already raised their price. So it's roughly like, what, $2.5 per gram. And yeah, just you do the math. But they are quite conductive. And then if you do it right, you could, you can have like a actually very decent 3D printed circuits inside of your components. Another thing I didn't show here because I think the company went bankrupt or whatever. So there used to be a company that does conductive silicon print. So essentially, you can print flexible and stretchable circuits in a silicon form factor, and together with non-conductive silicon. So yeah, it's pretty decent, but they charge a lot of money to do that. And you have to send in the design files for them, and then they print out to you for you, and then send it back. Some other methods, we can also use like laser cutting plus rastering. Rastering basically meaning, so laser cutting, usually you have the cutting through mode. You can think about like just like cut through the entire whatever materials there. The rastering is essentially doing like, it's like standing away, or like doing a lot of paths that going back and forth around that area. So we can use that plus some plug and place for silver inks. Let me just show you how it was done, actually. So we could have the so how it was done is basically we have the laser cutter to cut out. This is acrylic board. So acrylic will have you can have essentially cut out the object shape, and then we add a additional dispense for like a syringe design for the nanoparticle silver paste, and then they can use the laser when they're in defocused mode to essentially heat up those traces and then make them curing and become conductive and stable. And because the laser cutter is essentially like a XY planetary machine, right? You can also just add like a place and drop components to this to just place each of the components needs to be soldered or connected to the circuit, and use the laser to solder the entire board for you, essentially. And it gives you like a cool effect because once everything's connected, obviously you connect the power line the last, and then the whole thing flies out. Is it flying out? Okay, there we go. And there are some more like, I guess, avant-garde methods of doing that. You think about dispensing the silvers onto acrylic or onto the wall, onto a couch. Why can't we just dispense it on the human, right? Doesn't hurt. Your skin is also a canvas, and people draw a lot of random things to it anyway. So, they have this very interesting project. It's called body printer. So essentially, it just, similar design method as you would do with like a normal PCB design. Just draw the circuit, SVG files or XML files, whatever, and then, oh yeah, you do have to clean your skin a little bit before that. And then and then you just chose your layout. Obviously, they chose one of the easier layout for demo. And okay, and essentially, this little machine is gonna come down to the right spot and then start to ejecting out those obviously very safe inks onto you, and then let it cure. So you can have a circuit onto you as a tattoo, essentially. So yeah, pretty neat, right? And stretch, anything you can imagine. And if there's any people touching you, you can even build your own I guess a small EMG sensors or something. essentially anything that needs an electrode, you could potentially do this through this method. And of course, they put some LEDs to just for show. You will notice that cheekily, they usually just use LEDs for show because chances are these type of conductive inks are not that conductive to drive, say, like I2C or SPIs. But just for lighting up LEDs or sensing if there's something touching it or is there any like shape changing on the surface, those inks are typically, pretty good to do, pretty good enough to do. So yeah, I hope that was fun. If you are interested in this type of class, this type of things, you can feel free to take my class next semester as a special topics. Okay, so that's the end of the PCB design plus some other stuff. Thank you for coming, and we will look forward to listening from you guys next lecture.